So, let us start recalling our previous lecture. In the previous lecture, we had started looking at the properties of local maxima minima for functions of one variable. In particular, we looked at the following theorem, namely, if f is a function which is defined on a open interval a b to r and c is a point in that open interval. Now, if c is this point which we have selected in a b is a point of local maxima or a local minima, then f dash of c exists and f dash of c exists, then f dash of c is equal to 0. So, if two conditions are satisfied, namely c is a point of local maxima or minima and the derivative at that point exists, then the derivative must be 0. Geometrically, that meant the tangent must be horizontal. And we also pointed out that the converse of this theorem need not hold, namely the derivative equal to 0 at a point need not imply the function has a local maxima or minima. We had given some examples. Here is the graph of f of x is equal to x cube. This graph is on the positive side, it is positive, it becoming flatter and flatter, and turns negative. For negative values, x cube is negative, so it turns around. So, the at 0, the x axis is the tangent to this curve y equal to x cube, but at this point you can obviously see that there is no maxima or minima, because at all points nearby on the left the values are smaller and all the values of the function at points on the positive side they are positive. So, they will be bigger than the value at the function at the point 0. So, this converse of this theorem need not be true. So, that is one observation, and secondly, the theorem holds only when C is a interior point. So, keep in mind there the interval is a b, open interval a b, and the function is defined on the open interval a b. So, this need not hold the conclusion that C is a point of local maxima or minima and the derivative at that point exists. This need not hold if the interval is having endpoints. So, for example, let us look at this example f of x is equal to x if x belongs to 0 1. So, this function y is y equal to x and this is the graph of the function. So, the function has got is 0 at 0 and is 1 at 1. So, if you look at the neighborhood of 0 in the domain of the function, on the right side the values are positive. So, they are bigger than 0. So, 0 is a local minima and 1 is a point of local maximum. But if I look at the derivative of this function from the left or from the right, the derivative is equal to so, at this point the only possibility is derivative of the function from the left side, or and 0 the only possibility is derivative rate of change of the function from the right side, both are equal to 1. So, the derivative is not equal to 0. So, the condition of saying that the derivative at a point of local maxima or minima should be 0 is valid when our domain, the point where we are analyzing is in an open interval. So, that was the second observation we wanted to point out. And also look at that we are saying that this is only a necessary condition. That means, the local maxima minima to occur, it is not necessary the function has to be differentiable. We are only, this theorem only gives you a necessary condition if the derivative exists at that point. But functions can have local maxima minima without being differentiable. So, let us look at, for example, the function f x is equal to mod x. The function f x is equal to mod x has got a minimum value at the point x is equal to 0, but the function is not differentiable at that point x is equal to 0. Right. On the left, if you look at on the left of this point x is equal to 0, the function is minus x. So, the derivative is minus 1. So, left derivative at the point 0 is minus 1 and the right derivative at the point x is equal to 0. If you are coming from the right side, the function is x and the derivative is 1. So, the function is not differentiable at the point 0, but still it has a local minimum at the point x is equal to 0. In fact, something much stronger can be said. Here this function is continuous at 0, but is not differentiable at 0 and has a local minimum at 0. Even we can define give examples of functions which can have local maxima or minima at a point without even being continuous at that point. So, that is also possible. For example, let us look at the function f x is equal to plus 1 at x bigger than or equal to 0 and equal to 0 if x is less than 0. Then the function has a local maximum at the point 0, the value is 1. So, for all points in a neighborhood of that point x is equal to 0, the value at the point 0 is bigger than or equal to value at every other point. So, the function has a local maximum at the point x is equal to 0, but f is not even continuous at the point 0. The left limit is 0 of the function at that point and the right limit is equal to 1. So, this function is not continuous at 0, but still the function has a local maximum at the point x is equal to 0. So, the existence of local maximum or a local minimum for a function has nothing to do with this property being continuous or property being differentiable. What we are saying is, in terms of continuity or differentiability, you can give conditions which ensures that a point is a local maxima or minimum. So, our previous theorem gave a necessary condition, and let us now state some sufficient conditions which ensure that a point which we are analyzing is a point of local maxima or minima. So, the theorem is called the continuity test. So, this says that suppose f is a function on a open interval a b to r and it is given to be continuous at the point c belonging to the open interval a b. So, if f is increasing in an interval in c minus delta to c, that means on the left side of c, if the function is increasing and it is decreasing in an interval c to c plus delta, which is a interval on the right side of c, then f should have a local maximum at the point c. So, this is the mathematical way of saying that if the function is rising on the left and falling on the right and it is continuous at the point c, then it must have a local maximum at the point c. So, the geometric visualization that we have of local maximum is translated into this property. Namely, so this is a sufficient condition that if function is continuous at the point c, on the left of c it is decreasing, on the left of c it is increasing and on the right of c it is decreasing, then it has a local maximum at c. So, there is a parallel condition, a similar condition for local minimum, which says that if f is decreasing on the left side of c, so that is in an interval c minus delta to c, and is increasing in an interval on the right side of it, that means in an interval c to c plus delta, then it must be a local minimum of c. So, if both these geometric visualizations translated into mathematical concept are true when f is continuous at c, right. So, do not make a mistake of saying that on the left it is increasing, on the right it is decreasing. So, it must be a local maximum. That happens when you have a condition satisfied that the function is continuous, and similarly for decreasing. So, this is what is called the continuity test for increasing and for continuity test for local maximum and local minimum. We can also say we have a theorem in terms of the first derivative, what is called the first derivative test. If you recall, we proved that if the derivative of a function, in the previous lecture we had proved that if the derivative of a function is bigger than 0, then the function is increasing in an interval, and similarly if the derivative of a function is less than 0, then the function must be decreasing in that interval. So, that property together with the previous theorem gives us what is called the first derivative test. Suppose f is defined in an open interval a b to r and c is a point in the open interval a b such that f is continuous at c. So, continuity is always going to be a condition. Okay. So, suppose there is a some delta bigger than 0 such that the derivative exists in an interval around C, but may not be at the point C. So, this is written mathematically as there exists some delta bigger than 0 such that if we look at the intervals open interval C minus delta to C union the open interval C to C plus delta, then the derivative exists in this interval. That means, at every point on the left of C and on the right of C in this interval the derivative exists. So, that is one part of the condition, and second thing is if the f dash of x is bigger than 0 on the interval C minus delta to C and f dash of x is less than or equal to 0 in the part C to C plus delta. So, that will imply by the previous theorems that if this is so, then f will be increasing on the left and f will be decreasing on the right. So, that will imply that it has a local maximum at the point C. So, the first derivative test requires two things. One, first of all the derivative the function must be continuous at the point C, and secondly in a neighborhood of the point C except possibly at the point C the derivative is bigger than or equal to 0 on the left and less than 0 on the right, then it has a local maximum at that point. And the second condition, similar condition is there for the local minimum, that there is a delta bigger than 0 such that the derivative exists in the neighborhood around C except at the point C. Such a neighborhood normally is called a deleted neighborhood, because this is a neighborhood around the point C of length C minus delta on the left and C plus delta on the right, and only the point C is omitted from it. So, from an interval C minus delta to C plus delta, if you omit the point C, you get a union of two disjoint open intervals. So, this is called the deleted neighborhood of the point C. So, the condition says there is a in a deleted neighborhood of the point C the derivative exists, and if we have derivative is less than or equal to 0 on the left and bigger than 0 on the right. So, that will imply the from the derivative conditions that the function is decreasing on the left and increasing on the right. So, it must have a local minimum at that point C. So, this is what is called the derivative test, first derivative test for analyzing a point to be a point of local maxima or minima. So, these are the sufficient conditions which ensure whether a point is the local maxima or minima. So, let us repeat once again. If you are able to say that the function is continuous at the point C, on the left of C the derivative is positive, on the right of C derivative is negative, then it has a local maximum, then it has. So, if those conditions are satisfied, then it has a local maximum. So, that point will be a point of a local maximum. And similarly, if f is continuous and its derivative exists in the related neighborhood with the property that derivative is less than or equal to 0 on the left and bigger than or equal to 0 on the right, then it has a local minimum at the point C. So, this theorem can be used to analyze whether a point is a point of local maxima or minima for a given function or not. So, one has to check all these conditions and then draw the appropriate conclusion. So, let us look at this function f of x is equal to x plus 2 into mod x, x belonging to R. Now, first of all, when you look at such a function, there is this term mod x coming, and we know that modulus of a number x is equal to x if x is bigger than 0 and it is less than x if x is less than 0. So, this function is continuous everywhere because it is a product of two functions x plus 2 which is continuous and mod x is continuous. So, this is the function which is continuous everywhere. Let us look at the differentiability of this function. It is continuous everywhere except and it is differentiable also everywhere except at the point 0. See, if x is not equal to 0, this function is either x plus 2 into x if x is positive, and this function is x plus 2 minus x if x is negative. And at the point 0, we know mod x is not differentiable. So, this function is not going to be differentiable at mod x. That is not the exact reason. The reason is, if we look at the left derivative and the right derivative for this function, they will turn out to be different. So, to see that, let us just analyze, because this is the first time we are coming across such an example. So, let us look at the differentiability of this function at the point. So, f of x, the function is equal to x plus 2 into x if x is bigger than or equal to 0, and is equal to x plus 2 into minus x if x is less than or equal to 0. So, for x bigger than or equal to 0, the function is f of x equal to x plus 2 into x. So, which you can write as x square plus 2 x. So, if I look at the derivative at the point 0, so what will be the value of the function at 0 is 0. So, what will be the f dash of at 0, and I am coming from the positive side. So, plus. So, that will be limit of x going to 0 of f of x minus f of 0 divided by x, and x positive. So, that will be equal to limit x going to 0, and when x is positive, the value is x square plus 2 x, f of 0 is 0 divided by x. So, that is equal to limit when x cancels. So, it is x plus 2. So, the value is 2. So, the right derivative at the point 0 is 2. Let us compute the left derivative of this at the point 0. So, for x less than 0, less than or equal to 0 does not matter, because the function is uniquely defined at the point 0. F of x is equal to x plus 2, and the mod x is now minus x. So, it is equal to minus x square plus minus 2 x. So, the f dash of 0 from the coming from the right will be equal to limit x going to 0 f of x minus f of 0 divided by x, x less than 0. So, when you put the values, so limit x going to 0 of, when x is negative, so it is minus 2 x minus of x square minus 2 x, and at 0 the value is 0 divided by x. So, what will be limit of this? Once you cancel out x, so that is equal to x goes to 0, so that is minus 2. So, when you look at the left limit of the function, that is minus 2, you will look at the right derivative at the point 0, that is 2. So, this function is not differentiable at the point 0. So, let us come back to the statement that for the function f of x is equal to x plus 2 into mod x, it is continuous everywhere and it is differentiable also everywhere except at the point x is equal to 0. So, let us look at the derivative of this function on the left side and on the right side. So, derivative, when the function is x is bigger than 0, the function is given by x plus 2 into x. So, what will be the derivative for all points on the right side? It will be 2 times x plus 1. So, which is bigger than 0 for all x bigger than 0. And similarly, if I look at the left side of this function, then the function is given by mod x will be minus x. So, it is minus x plus 2 into minus x. So, that will be minus of 2 x plus 1 for this is the type of where it should be less than 0. So, this point should be less than right, sorry. So, this is for all values x less than 0. So, on the right side the function has positive derivative, on the left side the function has negative derivative. So, this implies that f has a local minimum at the point x equal to 0 by the first derivative test. So, how is the first derivative test applicable? At the point x is equal to 0, the function is continuous. So, condition of continuity is satisfied. In the deleted neighborhood of 0, right, f dash of x is bigger than 0 if x is bigger than 0. So, the function is rising on the right side and it is less than 0 on the left side. So, it is dropping. So, by the first derivative test, the function has a minimum at the point x is equal to 0. So, that is how you will apply the first derivative test, by ensuring the continuity of the function at the point that you want to analyze, looking at the nature of derivative on the left of that point and on the right of that point. At that point, the function may not be differentiable, that is not required for the first derivative test. So, let us go a step further and let us look at what is called second derivative test. But for the second derivative test, I just want to recall what is called second derivative of a function and so on. So, there is a notion of successive differentiation. So, let us say a function f is defined on an interval I contained, and so the function domain is the interval and taking real values. So, I is an interval in the real line and f is a function defined on the interval. We say f is twice differentiable at a point C. So, it is said to be twice differentiable at a point C, which is inside this interval I. If f is first of all differentiable in an open interval around the point C in a neighborhood. So, first of all, this is a condition that f should be differentiable at all points in a neighborhood of the point C. So, what is a neighborhood? It is an open interval around the point C of length 2 delta. So, it will be C minus delta to C plus delta. So, f should be differentiable in a neighborhood of the point C 1, and so once it is differentiable at every point x in this interval, we will get f dash of x. So, f dash is a function now in the interval which is defined in the interval C minus delta to C plus delta. At every point the function is given to be differentiable in the interval C minus delta to C plus delta. So, f dash is a function and I can ask whether f dash is again differentiable at the point C or not. So, if there is a point f at the point C, f is differentiable in an open neighborhood of the point C, and the derivative function which is defined in that neighborhood now is again differentiable at the point C, then we say that the function f is differentiable, twice differentiable at the point C. So, it is some sense the derivative of the derivative function, but keep in mind to define that it is necessary that we should say that f is differentiable in an open neighborhood, then only that will make sense. So, twice differentiability means f is differentiable in a open neighborhood of C and the derivative function is again differentiable at the point C. So, we say f is twice differentiable at the point C, and this second derivative, this is called the second derivative of f at C, right. When f dash is differentiable, it will have a derivative, this f dash itself will have a derivative at the point C, and that normally we denote it as f dash dash, but that is shortened as f double dash at C. So, f 2 dash at the top indicates the second derivative. One also denotes the second derivative by d square f by dx square at the point C. So, the first derivative was df by dx, and now the second derivative is d square f by dx square. So, there is a notion of the second derivative. One can go on defining provided the higher order derivatives. The concept of n times differentiability and the nth derivative of f of c we can define provided. So, to say that f is n times differentiable, we should at a point C we should say that the n minus 1th derivative exists in a neighborhood of the point C and is there differentiable at the point C. So, that will denote f n c to be the nth derivative is denoted by this bracket at the top, the nth derivative of c to be defined as, look at the n minus 1th derivative, its derivative at the point C whenever defined will be called as the n times differentiability of the function. So, what will be the second derivative? Second derivative is the derivative of the derivative function. So, we won't have opportunity to use this, but it is interesting to say concept that if every derivative of every order exists for a function, then we say function is infinitely differentiable. If you recall, we had said that we will assume that the exponential function is differentiable, e raised to power x is differentiable, and its derivative is the function itself. That is what we had looked at as an assumption, and using that we had defined the derivative of the log function. So, exponential function derivative is itself, so automatically that is one example of a function which is infinitely differentiable. So, let us just conclude today's lecture by saying we have looked at the notion of differentiability of a function as the condition for analyzing local maxima minima. So, we had the continuity test for analyzing local maxima minima, and then we had the first derivative test for analyzing local maxima minima. We will state in the next lecture what is called the second derivative test for local maxima and minima of functions, sufficient condition in terms of the second derivative. Thank you.